In this objective, we're looking at 1.8 valence electrons and ionic compounds. So this learning objective states that we should be able to explain the relationship between trends in the reactivity of elements and periodicity. So the periodic table shows patterns in electronic structure and trends in atomic properties, okay? So the likelihood that two elements will form in a chemical bond is determined by the interactions between the valence electrons and the nuclei of elements. So remember, valence electrons are referencing the outer energy level, which is where you'll find those valence electrons, and they're used for bonding. So the number of valence electron tells us how many electrons are used for bonding, as well as making sure to reach that octet rule, okay? So the typical charges of atoms in ionic compounds are governed by their location on the periodic table and the number of valence electrons, okay? So looking at this right here, you can see based off the chart, I know yours will probably be in black and white, but the blue is considered variable charges. So they can have many different charges. The white unshaded is going to be fixed charges. So you can see like the first column, the alkali metals, group 1, they're going to have a +1 charge. Group 2, the alkaline earth metals, +2. And so here it's going to keep going on and on as well, all the way down to 0, which red is a special case. So our noble gases in group 18 are, since the octet rule is satisfied for group 18, they're not going to have a charge of, they're just going to have a charge of 0. And essentially these charges, just making sure I clarify well enough, these are the charges as an ion. Okay, I do want to note that these three right here, I'm going to zoom in a little bit, have a +1, +2, +2. So that +1 corresponds to silver. Silver has a +1 charge. This one right here corresponds to copper sorry, not copper. This corresponds to zinc. Sorry, copper's right here. This corresponds to zinc +2, and this right here is cadmium +2. These do have fixed charges, and one way I kind of remember it is since silver is in group 11, I think, ooh, there's one of them +1. And then for group 12, I memorize it by saying, ooh, we're in group 12. There's 2 of them with a +2 charge. That's kind of how I memorize it. You will notice that there's blue underneath here as well, because that ends up being the post-transition metal. So they can have many different charges, okay? Last thing that I want to add, if you can just make a quick, brief outline of the periodic table, I wanted to show something based off metallic and non-metallic character. Please note where we have our staircase on the periodic table helps us divide what's a metal, what's a non-metal, and what's a metalloid. So looking at that little staircase I just did, and I'll also do it here as well. And again, this is I don't know, this is not to scale. Here, that staircase helps divide the metals and non-metals. So generally, elements touching the staircase are going to be our metalloids. Remember, they're going to have both properties of metals and non-metals. So here, everything over here will be metals, and everything, sorry, that's to the left of the staircase, and everything to the right are going to be our non-metals, okay? So when we talk about metallic versus non-metallic characters, when we move southwest on our periodic table, or you can say moving to the left going down, we're going to increase in metallic characters. Again, then we're getting more of a metal. And then when we move to the right, we start to increase in non-metallic characters. And again, this is meaning towards those nonmetals. And you can even reference electronegativity with this. So going based off how the typical charges of atoms and ionic compounds are governed by location and number of valence electrons, I want us to take a peek at group 1 in 17. So if we know group 1 has a +1 charge and group 17 has a -1 charge, it's always going to be a 1-to-1 ratio, as in for one alkali metal and one halogen will make an ionic compound. So like NaCl, lithium fluoride, potassium bromide, it will always be 1 and 1, okay? But if we look at, like, for example, group 1 and group 16, that is again, +1, and 16 is going to have -2 charge. Here, it's always going to be a 2-to-1 ratio. You're always going to need 2 alkali metals for one of the chalcogens, okay? So here, we have Na2O. So again, 2 alkali metals for the one chalcogen, lithium, 2 sulfide, and whatnot, okay? All right, so let's look at problem 1 together. So based on the position of elements on the periodic table, which of the following pairs contain compounds that are most likely to have similar chemical properties, okay? So let's look at the first example, SeO2 and TiO2. So first off, selenium and titanium are going to be in different areas on the periodic table, okay? So I would say this is definitely, I'm gonna do this in a different color. This is definitely gonna be no. So although they both have oxygens, it's the issue of that selenium is a nonmetal and titanium is a metal. So I would not think that these two compounds would have similar properties whatsoever. Our next one, we have calcium carbide and calcium fluoride. So here, the fact that they still have calcium, like, that's awesome, love it, but it's the issue of the carbon and the fluoride, okay? Here, that's going to be causing even though they're both non-metals, I wouldn't, if let's say that carbide was in the same group as the fluoride, I would say that they would be fairly similar, but it's the fact that those non-metals are coming from different groups, okay? So no, although both have calcium, and I mean, granted, yes, the carbon and the fluoride are both nonmetals, they're just from different groups. And both C and F are nonmetals. It's the issue that C and F are from different groups. So again, you can't say just because the carbon and the fluoride are both nonmetals that they're still going to have similar properties, okay? All right, next one we have magnesium chloride and magnesium fluoride. So here, they both have magnesium, and here both have a halogen. Again, that halogen being the chlorine and the fluorine. So the chlorine and the fluorine are coming from that group 17. They're both going to have similar properties. So here I would have to say that C is going to be my answer, but let's just check with D to prove why D will not be correct, okay? So D, I have SCCl3 and PbCl3. So they both have chlorines, okay? Oh, let me do it. Same red. So both have chlorines, but the issue is the scandium and the lead are going to be found in they're found in the same block, but they're going to actually be found in technically different groups and different charges. So here both have chlorine, but the issue is scandium and lead are in different sections of the same block. The reasoning for that, scandium is in transition metals and lead is in post-transition metals. This is kind of a relatively tricky one. So again, even though they're technically still found in the transition metals, it's the fact that the lead is in technically the post-transition, while scandium's found more in the transition. So yeah, that would make C the answer. Both magnesium, Cl and F are in both the same column, same group. And also that's another catch. It's the fact that the scandium and lead aren't technically really in the same group, okay? All right, problem 2, why don't you pause the video and try this out yourself. So in this problem, you have properties of the compound sodium sulfide are listed in the table above. Here it told us it's a yellow powder. It told us its solubility. And I know we haven't talked about solubility yet, but it's more just like they're giving you kind of some background. And it has its melting point, which is relatively high. And this makes sense because it's an ionic compound. So on the basis of periodic properties, which of the following compounds should have properties that are most similar to those of sodium sulfide? So here, again, think about groups. So here I have carbon disulfide, or you can say, well, essentially this can be, carbon sulfide. So no, carbon's from a different group and considered more non-metal than the sodium. So I would say this is not it. Here, barium sulfide, I would say no, because barium's from group 2. Sodium's from group 1. The next one, copper 1 sulfide. No, copper is from the transition metals. But I would say D is the answer, because potassium is also in the same group as sodium, which is in group 1.